Hello, my name is Virgil Goldberg, and this is my Physics 2212 Lab 5 on Faraday's Law. So the purpose of this lab is to analyze the effect of Faraday's Law. So we will be analyzing it and seeing its effect through a falling magnet inside of an aluminum pipe. And the goal is to compare an experimental result to a simulation and see what real-life impacts it can have on Faraday's Law. And we'll see that the main result is that the average fall inside the real tube is of about 0.64 seconds, while the model gives us a time of 0.57 seconds, so a slight difference. So here are the key concepts. We have the magnetic flux here, so it's the magnetic field going through a certain area, so it's the magnetic field times an area. The induced EMF is the change of magnetic flux over time. And the magnetic force can be calculated from the current times the length of the current going through, cross product with the magnetic field created. And to find this current, we can use I equals VR, so V being EMF and R being the resistance of, for example, the tube or the coil. So here is the real-life experiment. The system is the bar magnet that we can see here. And the forces acting on it are the gravitational force and the magnetic force. And we'll see that the F net will be going downwards as the magnet keeps falling. The surrounding is the tinfoil roll that is represented by these two lines. And so what we do is we drop the magnet the north side down first, and we count the time until it reappears from the other end of the tube. And we make the assumption that there's negligible air resistance and fluctuation in the aluminum tube. So here are the main results. We see that the average fall speed is of 0.64 seconds. Here are all the different values of the aluminum coil and of the magnet. So these values were calculated in Lab 3 previously a few weeks ago. So here is the code for the simulation. So here on the left, we can see all our constants that we've just found previously right here. So we plug them in here. This here is used to calculate the magnetic field from the dipole moment using this equation that we used in Lab 3. And then here is used to calculate the change in magnetic flux over the change in time. So this is basically using this formula and rewriting it to be depending on time, so using the value of V to show a change in the distance R. So here are the results from the simulation. So we can see that it is in the tube for 0.572 seconds. So this is using the magnetic dipole of 1.675 that we found from Lab 3. So we can see that there is a slight difference from the 0.64 second fall that we've seen in the real-life experiment. So there could be several reasons for this. One is that there is friction and air resistance in the real experiment because the magnet did not fall perfectly straight. It did hit a bit of the walls, and there's always air that creates air resistance. There's also human error. Well, even though I used the video, you don't see it perfectly, we'll say, straight. So there is a slight, we'll say, vision angle dead space that probably made the fall slightly longer. So as an extension, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So if the resistivity is close to zero, then the resistance is almost zero. And from I equals V over R, we see that a very small r will result in a very big current. And a very big current results in a bigger magnetic force, braking force. So this will mean that the fall would be much slower. So what if there's holes and slots were cut into the tube? Well, a tube is just a series of rings on top of each other. And holes result in less of those rings being complete, so the current has a more difficult time passing through the tube. And so less rings means less current, therefore less magnetic braking force, and therefore a slower fall. Thank you very much.